again. Welcome to our flue gas CCUS webinar. We are very happy that you decided to join us this afternoon, and we hope that you will have a great experience. The agenda for today is really focused on flue gas CCUS. So I'm going to give you an overview of what it actually is. We are going to talk about flue, the importance and the steps of flue gas pretreatment. So we will be looking at SOx and NOx removal. Then we'll look into the CO2 capture unit, the core unit itself. We will look at different types of solvents and process setups. Then we'll have a look at CO2 compression, and the last step is CO2 storage and utilization. And at the end of the webinar, I'm going to share with you what other materials you can use to educate yourself and how we would love to help you train in flue gas CCUS. All right, so what is actually CCUS? The letters, they stand for carbon capture, utilization, and storage. Now, the capture part, that's basically you need to capture the CO2 from the exhaust gas, and you refine it and you capture it. In the utilization part, you're trying to use the CO2 as a material in products with some market value. And in the storage, you are trying to store the captured CO2 on the ground and offshore to make sure that it's not released back in the atmosphere. Now, in terms of where is the CO2 actually created in industry or where do we want to capture it from, there are different places from where CO2 capture is considered. And now these different sources, they are giving us CO2 at different concentrations, at a different total pressure, and that basically translates to different partial pressures of the CO2. And depending on those partial pressures, that will dictate the choice of the technology we are going to use for capturing CO2. Now, there had been talks about direct air capture. The big challenge there, of course, is that the partial pressure of CO2 is very, very tiny, as you can see in this table. Then the yellow part, that's what we are going to be focusing on right now. We are going to be focusing on the point source carbon capture. First, the source can be power generation. So either coal-fired power generation where we get the highest concentration of CO2, or natural gas power plants where we get lower concentration. We could also mention biomass power plants, which are actually potentially carbon negative. Another source is the cement production, where we, of course, combust fossil fuels. So that's where we get our CO2. And also the calcination process, so decomposition of limestone, that also release some emissions. Another industry would be the steel production, so from blast furnaces and basic oxygen furnaces where coal is used as the reducing agent. We also get the CO2 emissions. And we could also mention waste to energy plants, so that when burning the municipal waste, that's where you also get CO2, which you could capture. As we can see, the different sources, they deliver CO2 at different concentrations, and they also come with different levels of impurities. So those impurities, they will affect your carbon capture, and we need to make sure that they are removed before sending the flue gas into the CO2 capture unit. Why? So for example, the SO2 and SO3, so the SOxes, they would form heat-stable salts with amine solvents. NOxes, they can form nitrous amines or degrade the amine solvents, which are being used. And high level of oxygen, they can also oxidize your solvents. So if you want to make sure that your solvent is not going to be run out and you will not have it degraded, you have to make sure to remove those impurities. And you can see in the table here that really different sources come with different levels, different challenges. So what I'm going to do right now, I'm going to give you an overview of what are the different steps of the total flue gas CCUS. And for that, since our main product, our company, we are brine research and engineering, and we do have a ProMax simulation software. I'm actually going to go into one of our example files. So right now I'm opening ProMax 6, which is the current version of ProMax, and I'm going to open one of our example files. So for anyone with ProMax installed on your machines, you're able to access these files as well. The file I'm going to look into is to be found in the sustainability folder. So I'm going to go into the sustainability folder, and I'm going to go into the carbon capture folder. And the one I want to be looking at right now is going to be this carbon capture from cement plant flue gas. So let me open that one. This file has, as you will notice, this file will have multiple flow sheets. So these multiple flow sheet, each flow sheet will show us one portion of the whole path for CCUS. So the first one we are starting with is the pretreatment flow sheet. So this is where we get our cement plant flue gas, and we are sending it into a pretreatment section. Now this pretreatment section, this is a DCC, direct contact cooling tower, where we use fresh caustic as well. And the caustic is going to help us capture SO2 and to remove it to a very small level. And as you can see, coming in, we have about 50 ppm SO2. Coming out, we are able to get to 2.3 ppm SO2. And as the name of the unit suggests, DCC, direct contact cooling tower, we are also bringing down the temperature, 135 down to about 60 degrees. So from the pretreatment section, we are sending this stream to another flow sheet. In this case, this is the amine unit. So this is a unit where we are going to be capturing our CO2 using amine solvent. This is done in the following stages. In the first one, we are contacting our flue gas with a solvent. In this case, it's MEA, in an absorber column. The cleaned gas goes up, and you can see the concentration of CO2 went down significantly. And what we are getting down here is a rich solvent, rich in CO2. And that solvent is being sent to a regeneration section where we are applying heat to release the captured CO2, and then we are able to send the lean solvent back. So this is our amine unit, the capture, the core capture unit. The CO2 is then being sent to another flow sheet, and in this one, we are compressing the CO2 to a high pressure in order to send it through a pipeline to an injection site. So you see this whole process of carbon or pretreatment, carbon capture, and compression and transportation is being modeled in one complex model. The reason we are dividing it into multiple flow sheets instead of having one big paper is that it allows us to select the appropriate thermodynamic model for each process. So each of these processes require the best thermodynamic model for what it needs. And we are going to discuss throughout the webinar what those thermodynamic models are. All right, so this was our, let's say, overview of what the processes are. Right now, what we're going to do, we are going to go and focus on each of these steps separately. So this brings me back to slides. Let's first discuss the first important step, and that is the flue gas pretreatment. So the common pretreatment steps are first, particulate removal. So if there are any particles present in the flue gas, they need to be removed either using, let's say, electrostatic precipitators, fabric filters, cyclones, or any of these, just to remove the particulate. Another step is usually desulfurization. And the pretreatment solvent for the desulfurization is usually caustic solution, as we've seen in the example. It can also just be a plain water or seawater. We have cases where using ammonia. We can also use limestone slurry or sodium carbonate or sodium sulfate, as you can see in the list here. For NOx removal, there are two ways how to control the NOx emissions. One is actually an in-combustion control. So that's where you control it already in the combustion. That's where you get your flue gas from by using low NOx burners. Or if you are controlling just after the combustion, what would usually be used is either selective catalytic or selective non-catalytic reduction. What it is, it's basically a process where you reduce your NOx to nitrogen using either ammonia or urea. Another option for NOx removal could be also wet scrubbing. So that would basically be the same process as we use for the SO2 removal. And last step of the pretreatment is that we want to make sure that the gas is cooled and we're controlling the humidity of the gas by lowering the temperature, which is to a temperature which is optimal for the CO2 absorption. So what we're going to be looking at, what you're looking at right now, it's a bit of chemistry. So if you guys remember a chemistry class from your studies, this is what happens to SO2 when it comes into a solution. So you can see that SO2 and water, we are forming ions, so HSO3 minus and H plus. And so that's the first portion of the reaction. The last reaction on this page shows you what happens to SO2 when it's being oxidized. So we are oxidizing it to H2SO4. So this is what happens to SO2. And what I would like you to remember is that there are ions. This is going to be important for the selection of the thermodynamic package. And what I would also like to help you remember is that in this first portion of the reactions where there is no oxygen, no oxidization involved, the sulfur is not changing its oxidation number, all right? So it's 4 in SO2 molecule and both in HSO3 minus. It's just oxidation state 4. Here, when we use the oxygen, we are, of course, changing the S oxidation state to 6, all right? But in this first portion, no change of oxidation state, just forming ions. Now, what happens to NO2? In case of NO2, you can see that in NO2, if we look at the second reaction, NO2, the nitrogen is actually going to change its oxidation number. So while in NO2 molecule it's 4, when it goes to HNO3, the oxidation state is 5, whereas in HNO2 is 3. So again, there is a change in oxidation number. And we can see there are some reactions of also including reaction with oxygen. But again, what's important for us in terms of modeling, there are ions present. So I've got an example file here with 4 different processes of how to remove either SOx, but also NOx as well in one of the examples. So the first one we are looking at right now, this is a caustic treater, where we are actually also using oxidation air. And what we are looking at right now, we have a flue gas coming in into a contactor tower, and we are sending there a solution of caustic. This solution of caustic is being recirculated. We are always purging part of the solution and adding a fresh caustic here at the top. After the contactor, we also have an oxidation zone. So we are using oxygen to oxidize the sulfur from the state 4 to 6. And to be able to model it, we have a reactor here, which will help us model this reaction, all right? And what I would like you to take from this is how to model these reactions which are involving ions. So in ProMax, we do have a package, thermodynamic package called electrolytic package. This electrolytic package will help you look at the ionic level. So as we've seen in the reactions, ions were present and they are important for these processes. So we need to be able to model the process on ionic level. Therefore, a general equation of state would not be sufficient. If I go to active environment, I will be able to check, if I go to property package, that right now the package I'm using is called caustic treating PR. And you might be wondering what that actually is. If I hover over it, this small window will appear, and you can see that for aqueous liquid, if it's using a caustic treating package. And again, you might be like, what is that? We have a very good and extensive help written in ProMax. So I just hit F1 on my keyboard and I'm accessing help. Over here, we have this page called Physical Property Package Applications. In these, we have a list of the different models available in ProMax. And if I scroll down, there is this section called Electrolytic Gibbs Excess Activity Coefficient. So all these packages mentioned here, they are suitable for modeling ionic level. And one of them is the caustic treating. If you're interested in more details on this package, there is a full help page talking about this package in detail. All right. So in the contactor, we are capturing this SO2, and when being in contact with air, we are going to model the reaction. And the reaction we are actually modeling over here is this last reaction. So SO2 plus oxygen plus water, and we are creating H2SO4. This reactor, if I open it and I go to process data, it's really just being modeled as a conversion reactor for a reaction set I have created previously. That reaction set is called sulfide to sulfate. And if I want to look at the details of the reaction, I'm going to click on this reactions. And over here, I can see that I set a conversion of 40%, and we have a reaction equation here. Now, this webinar is not meant to be like a hands-on training where I would show you on where to click and how to do everything in terms of to model these. This, for example, creating reactors and creating reaction, this is something we always teach during our hands-on classes. And we actually have also some YouTube tutorials. So there is actually one YouTube video which really focuses on reactors. So if you're interested in more details on reactors, I definitely encourage you to watch this webinar. What I wanted to show you here is that if I open S-Stream, So let's see, for example, stream 14. And if I look at a composition, I'm able to see a composition. Now, this composition is not telling me anything about ions, right? It's kind of like it's thinking the SO2 is not dissolved. It's still showing as SO2 over here. All right. But the software under the hood knows that SO2 is not present there as a gas molecule, right? It's being dissolved in the aqueous phase. And if we want to find out what's the concentration of different ions, we have a very easy way to do it. If I go to analysis, we can create an ionic info analysis, which if I solve it, it's going to give me a list of ionic composition. So list of what's the actual composition of the different ions. And this is where you can see that the SO2 is actually present there as HSO3 minus and SO32 minus. And since we've already went through the reaction, we actually converted the sulfur into the H2SO4 state. You can see that that's where we get the highest concentration. It's now being present in the HSO4 minus and SO42 minus ion. All right. We are also able to look at a salt composition. So here, the different ions are recombined into salts, and we can see here their concentration as well. And this is actually one of the reasons why we also have to, of course, purge the stream, because we cannot have the salts, or the ions being accumulated to a level where the salts would precipitate. The next example I have here is an example of using not caustic right now, but using limestone. So if you guys don't know, limestone is basically CaCO3. That's a limestone. And in many instances, limestone slurry is being used to remove SO2 from the flue gas. Now, whenever you want to model a salt, and you know that the salt is actually being dissolved in the water into ions, you have to add the salt in your simulation as a combination of the acid and base. Because, for example, for CaCO3, if I go to active environment, I am able to find directly CaCO3 in my component list. You see, it is there. But if I add it in my simulation, ProMax will not be able to, on its own, find out what's the concentration of the different ions forming this salt. Okay, so if I want to model this salt's behavior in an aqueous solution, I need to add it as a combination of acid and base. However, we have a very nice tool to help you figure out what that combination should be, and that is our salt example. This salt example can be found under more shapes and ProMax property stencils. There is a group, there is a stencil called salt example over here. Once you take it and you put it on your flow sheet, it will appear over here, and it will ask you into which stream do you want to input this concentration. So in our case, it would be the COCA3 slurry. Click OK. It would ask us which salt do you want to model. And there is a list of all possible salts. So in our case, CaCO3. We need to put the weight fraction of the salt. So in our case, it's 15%. And then it would just figure out on its own how much of carbon dioxide and calcium hydroxide should be in the stream to actually form that salt. And on its own, it went and it put those numbers into the stream concentration. All right, let me just recalculate it. And now to show you a proof that it's really at 15% now, if I go to that stream and I go to analysis and the ionic inflow analysis, and I go to salt composition, there is CaCO3, where is it? Over here. And we can see that its salt mass fraction is 14.7%. So those would be the 15% we wanted. All right. Now, the process itself is very similar to what we've seen with the caustic. We are circulating the solution. We are absorbing SO2 into that solution. And in the oxidation reaction where we are using adding oxygen, we are oxidizing it into the SO4 ions. And again, there is a purge going out. And you see that the salt we are creating is CaSO4, which is gypsum. And then it's being recirculated, so we don't have it. All right. If you don't see the property stencils, they are, if you click on the more shapes, you will be able to activate them. Okay, so that's our limestone process. Now the third example I wanted to show you is a seawater example. So in this case, we are just circulating seawater, and the seawater, if I open the stream, is again being defined as a combination of acids like HCl and base like NaOH, where these two form the salt NaCl, and they are being defined here. For the seawater, you can of course come up with your own concentrations. There are numerous ways of how to find what your seawater concentration, the ionic concentration is. And we do actually have a seawater component in ProMax. So if I go to active environment, I'm able to search for seawater, And you can see that I have two seawaters here. One, it's for modeling non-electrolytic processes, and the second for modeling electrolytic processes. And that's actually the one we would want to use here, because, as I said, we care about the ionic level, okay? But other than that, a very simple process, which also helps us bring SO2 down. All right. The last one I have prepared here is a bit more complex, because in this case, we don't just have SO2, but we also have SO3 and NO2. All right. So for the SO2, SO2 behavior in water is just being taken care of by the electrolytic package itself. For NO2 and SO3, that is not the case. Okay. And how do I know? I know because I worked with ProMax for a long time, but how should you know, or how would you know? The best way to see which compounds, which acids and bases ProMax's electrolytic package takes care of its own, so their dissolution into the ions, is if you have a look on our help page, which is called Acids and Bases Supported by Electrolytic Models. This will give you a list of all the acids and bases which dissociate in water to form ionic species, and ProMax is taking care of it. And this is where you, of course, find things like carbon dioxide or carbonyl sulfide, all the different acids. But also that's where you find your sulfur dioxide. So that's what we were talking about for now. But you do not see here SO3, and you do not see here NO2. However, what you see here on the list is a sulfuric acid, and then nitric acid and nitrous acid. So those are the acids these oxides, the SO3 and NO2, actually go into, right? So if we wanted to model their capture as well, or their dissolution into the water, their correct ionic behavior, we would need to help ProMax a bit. And the way you help it is that you can create these reactions on your own. All right? And the way it's very simple, as I said, we would have to create the reaction. And for details on how to do the reactions, you can watch the webinar. But then once you have these reactions, if we open the column itself, we are able to go to process data. And here on the left, there is a possibility to select user reactions. And this is where I could switch on any type of reactions on throughout the whole contactor. So you see over here, I'm helping ProMax to understand that NO2 will actually change to HNO3, and then SO3 will change to H2SO4. And then ProMax is already able to take care of the dissociation of those acids on its own. So we are able to model the reactive distillation for those. And this will result in as having a model of how well the caustic solution in this case is going to be removing SO2, SO3, and NO2. And you can see that all of them, their concentration goes down. All right. So those are examples we have created for the flue gas pretreatment. As I said before, ammonia is sometimes used as well for the SO2 removal, or natrium carbonate or natrium bicarbonate. So there are other alkaline compounds being used as well. And we are able to create examples for other processes. Now we want to focus on removing CO2. I mean, acids were removed from gases for a long time, right? In any gas plant, in refineries, we were always removing H2S and CO2 possibly as well. But all these processes, they were done at high pressures. And that gave us a broader selection of solvents we could use because the partial pressure was high. Now, at the low pressure of flue gas, we don't have such a wide choices, okay? So there have, I would say, the two, let's say, commercially available solvents, which have been, or one which have commercially available, which have been mostly used, is primary amine MEA. Now we do also see the AMP piperazine blends being quite used. But for the rest of the solvents, a lot of them are proprietary solvents. So I just mentioned few here: KS1 from Mitsubishi Heavy Industry, Cansol from Shell, CDR Max from Carbon Clean, OAZ Blue, BASF, S26, Aker Carbon Capture. Now, these proprietary solvents, they are not in ProMax. I mean, we would love to have them there. So if you guys are from any of these companies and you want to add your solvent into ProMax, we're happy to talk to you. Some of these companies, they use ProMax to model their processes, you know. But what I want to say is that carbon capture at low pressure, it's sort of a new territory, and you know, people are coming with new ideas, new technologies, and everything's changing quite rapidly. So if you guys want to add something on this list, let us know in chat. Maybe I forgot some you know, very good solvent. If you want to let us know which one do you think it is, let us know in the chat. I'll be happy to hear it. And as I mentioned, the absorbent selection really comes down to the partial pressure of the acids. So this table shows you that if we had high partial pressures, we could afford to use things like physical solvents. We could afford to use or high loading DEA. We could afford to use at a mid-range hot potassium carbonate or hybrids. Now, at the very low partial pressures, most of the times what you will end up using is amines or some hybrid solvents. So what is actually alkanol amine? It's amine with at least one alcohol substituent. The nitrogen there is to interact with acid gases. The OH group is there to increase water solubility and reduce the vapor pressure. Some examples of those, we do have primary, secondary, and tertiary amines, the primary being most aggressive. The deviation between these is how many substituents do you have. Now, an example of a primary amine is, as I mentioned, monoethanol amine, so MEA, or AMP, which is actually primary amine, but it's a sterically hindered amine. You see the molecule is quite big. So that's AMP. What is also being used in these solvents are some additives. And one additive specifically to mention is piperazine. So it's the cyclic molecule you can see here. When piperazine is being added, for example, to MDEA. So MDEA and piperazine combination would often be used for syngas treating, which is at a higher pressure than flue gas treating. But the piperazine is sort of an activator. It activates the amine solution to help capture CO2. And you can see it on the figure here on the left that the red line, when increasing the piperazine concentration, the sweet gas CO2 goes down. Now, we cannot, one, I would say, disadvantage of piperazine is that if you use it at high concentration and at very low temperatures, it can actually precipitate. So, you have to be careful if you're somewhere like really, really up in the north and you use it at very high concentrations. Now, how do the reactions look like? The CO2 reactions with amines, and now this is what would happen with primary and secondary amine. I mean, the first reaction, that's not happening with amines as well. It's just, reaction with water. That reaction is very slow, kinetically limited. All the three reactions below, it's where CO2 reacts directly with the amine. The amine needs to have at least one free hydrogen to go through this reaction. So that's why this only applies to primary or secondary amine. Tertiary amines do not have a free hydrogen where the CO group could go. But these reactions are, let's say, relatively fast. Now in ProMax, we do have a number of CO2 solvents implemented in ProMax. We do have a list of the traditional amines as MEA or MDEA or AMP. We do have other amines, as I mentioned, piperazine, AEP, or MIPA, and all these like cool names you can see in the list. We do also have amino acids, so glycine and sarcosine, which are sometimes being now used in combination with hot potassium carbonate. But we do also have a list of proprietary solvents from Huntsman, Dow, or Eastman. The way it works is that you as a user, you just see the proprietary name of the solvent when adding it into your component list. But under the hood, ProMax knows what these are and what is it chemically, and it's able to correctly model their reactions with CO2. We are also able to model some physical solvents like methanol, DPG, or PC. All right, now where I'm going to go I'm going to open a model. This model shows a power plant on first flow sheet. This is a natural gas power plant. So we are burning a natural gas, and we have a lot of heat integration. At the top, we get a hot flue gas. We are sending it to a DCC to cool it down. And from there, it goes to our MEA unit. I already gave you the bird overview of this unit. We have an absorber section where we absorb CO2. We have a regeneration section where we regenerate the CO2. As you can see, this flow sheet is not solved. We don't have green streams everywhere. Some things are not specified yet. And that's what I will show you quickly how to do now. So in this unit, we are going to be using MEA, so monoethyl alkylamine, at 30 weight percent. So that's something I'm going to just quickly specify in the makeup block. So that's where we specify what's the target concentration of MEA. And again, this is a webinar, this is not a hands-on training, so I'm going to go through the specifications rather quickly because you guys are not supposed to, follow me on clicking everywhere. So I've got a 30% MEA, and I'm going to circulate it at 580 cubic meters per hour. I'm cooling it down to the absorption temperature. Now, this absorber is a column rather high. So the height of this absorber is going to be 30 meters. I'm going to let ProMax calculate what the diameter will be in order to hit a certain fraction flooding. This absorber is going to use structured packing. As in the flue gas carbon capture, we want to make sure that we have as low pressure drop as possible. So structured packing is what's usually being used. So a 30-meter height, we are able to, right now I just use Sulzer Mellopec 250, but we have a huge list of packings from Sulzer, Koglich, Rushik, and you guys are welcome to choose any you like. What's important for these carbon capture units is that we are able to correctly model the reaction kinetics of CO2 and those various amines at various temperatures and pressures, etc. ProMax is going to take care of it automatically if you select the electrolytic property package and if you select this column type called T-Suite absorber stripper. If you do these two things, it will correctly model what's the equilibrium concentration of those ions and how fast these reactions go, all right, at your conditions. So the user is not asked to put in the reaction kinetics for the CO2 reactions. So that's our T-Suite absorber stripper. We have a 30-meter column, so rather high. And the regeneration is being done at a pressure of 2.4 bar. So right here, I'm going to say that this is a 2.4 bar. And I'm going to say that I want to use as much steam or as much reboiler duty to achieve a lean loading of 0.2. Loading means how many moles of CO2 are loaded on moles of amine. And I can control the stripper behavior based on that. So I'm going to create a specification, which is going to be component ratio. I'll call it lean loading. This is going to be a lean loading at the bottom so where the solvent is lean, it's going to be in the liquid phase. And the components are CO2 versus MEA. And my target is going to be 0.2. Okay? And then I'm going to make that as specification. All right? So this is my specification now. And you see that once I put in all these numbers, the streams are kind of brownish or maroon. And now it's ready to be solved. So I'm just going to click execute. And right now, the simulation is starting. It's taking into account the numbers I put in, and it's going to solve. All right, so right now, it's solved. I can see that initially I had about 4% of CO2. I was able to bring it to 0.2% of CO2. Now, two things anyone with who's dealing with carbon capture units is interested in is what's your CO2 recovery and what is your specific reboiler duty. So let's first focus on the first one. What is our CO2 recovery? Meaning, how much CO2 am I recovering in this acid gas stream versus how much CO2 came in? And ProMax is calculating that on its own. If I go to Project Viewer, and down here, I will go to recoveries, and I'll go to MEA recoveries, because that's my flow sheet, and then results. And I can see here that my recovery is 95%. So 95% of the CO2 goes into the acid gas stream, which I believe it's pretty good recovery. I mean, depending on, what you need, but 95%, I think that's generally quite good. Now, what is SRD? I just mentioned. SRD is a specific reboiler duty. What that basically means is a ratio between energy supplied versus how much CO2 you captured. The units commonly used are gigajoule per ton of CO2. Now, I could just take a calculator, and look at gigajoule here, and then the tons here, and just, calculate it kind of manually or calculator. But I can have ProMax calculate it for me. And that will be if I go to Project Viewer, and I will create a user value. So user value is something, I can create on my own, a value variable, which is not inherently in ProMax, but I can just create it. So I'll do one, which will have units gigajoule per ton. I will call it specific reboiler duty, and I'll click OK. And now I'm going to have it calculated. So I will right click and I will create simple specifier. So this will be my SRD. And it will just be a ratio of reboiler duty divided by CO2. Now I'm going to quickly define what reb duty is and what CO2 is. So reb duty is a Q6. So reb duty is my Q6 energy stream. And I want to do it in gigajoule per hour. And then I want to define what a CO2 is, which is acid gas total composition mass flow CO2. Again, I'm doing this rather quickly. This is just to show you that there is this possibility, but this is something we, of course, teach step by step during our free classes. All right, but now you see when I did the ratio, I'm getting an SRD of 4.1. All right, so my SRD is 4.1. Now, generally, and again, it depends on a lot of factors, on how much CO2 you have, or what's the partial pressure of CO2 coming in. So at what concentration is it? Did you use a simple process setup, or did you do some optimization? But usually the reported SRD for MEA units is somewhere between 3.5 to 4.5 gigajoule per ton of CO2. Right now, with quite a low partial pressure, so I've got only 4% of CO2 coming in, and I'm able to get the 4.1 SRD for an 95%. Let me actually go and just put that note here that for MEA, I've got these results. So MEA, I've got 90% recovery and 4.1 SRD. All right, just a note for me. One thing we also have to pay attention to is that we are operating at low pressures. MEA is quite volatile. We are going to be losing some MEA. So let's have a look at what our amine losses are. The best way is to check how much MEA we actually have to be making up to be at steady state. So let me open this stream and composition and mass flow. So you see that we are actually losing almost 500 kilograms per hour of MEA. That's not optimal, right? So there are techniques of how to reduce the amine losses, and I'm going to mention them in a minute. All right, so this was our MEA. Now let's see. We would like to try using a different solvent. And in this case, what we would like to do is just check if something better can be achieved if I use the blend of AMP and piperazine. AMP and piperazine at the concentrations of 27% AMP and 13% piperazine. That's what's being also called Caesar 1, which is a solvent which has been I would say quite tested over the last few years. So let's see what happened to our unit if we go to AMP piperazine instead. So to make a quick change to the model, I'm going to add AMP and piperazine. So AMP is going to go in and piperazine is going to go in. And I'll click OK. And there will be just few things I will need to change. In the makeup block, so that's where I set the target. I'm going to delete MEA, so I don't want to have any MEA, and I want to do 27 and 13 of AMP piperazine. Since we have a higher amine concentration, right, 27 plus 13 is 40, we will use lower flow. So instead of 580, I'm going to initially do 450. And one thing I have to make sure is that I'm going to change the lean amine gas. So lean amine gas, it's a gas after recycle block. And I just want to make sure that I delete any residual MEA from here. All right, so I don't want to have, it doesn't really matter much. This is just a guess, but I just want to delete MEA from there. Okay, so we don't have any MEA in, we changed the concentration, we changed the flow rate, and one more thing to do, we are going to initially start at different lean loading. So 0.2 was what we used for MEA. Now for AMP piperazine, let's change that. First, this is not going to be ratio to MEA, but instead it's going to be ratio to AMP and piperazine. And let's initially go with lower. Now, the reason I'm going with lower is that it's easier to regenerate AMP piperazine than it is to regenerate MEA. Okay, it's more readily regenerated. All right, so let's now go and just solve it. So I changed the solvent. Of course, right now it might take some time to proceed because there has been a big change, right? It's changing the chemistry completely, let's say. So we'll see. Once it finishes, we'll look at it. All right, so now it's solved. I'm able to get to a much lower CO2 concentration. So let's actually have a look at what was, remember before we had 95% recovery? Let's see. Right now it's 99.5% recovery, so very high recovery. And our SRD right now is, all right, 3.6. So comparing to what we had before, we went to a higher recovery and lower SRD just by changing the solvent. Now, this column was before 30 meters. Let's have a look at the absorber. If I go to plots, this is where I'm able to look at temperature plots, but also at a component profiles. So let me just go and just look at CO2 profile. So you guys can see that the CO2 starting at those 4%, it goes rapidly down in the beginning. And here at the top, it doesn't really change much anymore. So it sort of tells me that the top portion of the column is actually not being used much. So I'm thinking maybe I could even do it with a smaller column. So let's try that. Let's go to our height. And let's go to, let's initially 25 meters. So we will bring the height of the column down. And again, let's check the profile. So you see that we cut the upper portion. I think we could go even lower. So I could go to like 18 meters. Now, you're completely right that a recovery of 99%, it's very high. Now, think about that, what our SRD is. Normally, the way these units would be optimized is that you would try to focus on lowering your SRD while keeping the recovery at kind of your target. So if your target is that the recovery has to be more than 90%, you will be able to get to even lower SRDs. And I'll show you in a minute how that can be done. All right, but now we were going down to 18 meters. Again, checking the profile, you see that we don't have this flat line here anymore. So we are able to achieve quite a good results with even shorter columns. Now, you see there is a lot of room for optimization. And there are many things you could play with. And that's where I would say a simulation software comes really handy because you are able to play with the certain parameters. So for example, here, I could try optimizing the flow rate and see if I could go with a lower flow rate. Of course, I will get lower recovery, but that's not really an issue. I don't need 99%, but it could help me with my SRD.
I would like to introduce to you the scenario tool, which is a great tool to run case studies. So whenever you want to alter one or more variables and watch the effect on your results, this is the tool to use. To open it, we need to click on the Add Excel Workbook tab on the left upper side. And once you do, it's going to open up an Excel file. This Excel file is an integral part of your ProMax simulation. So whenever you save your ProMax file, this Excel file will stay within it. Whenever you then open your ProMax file, this Excel file will open up with it. If I hit the X over here, it's actually going to ask me if I want to delete it. So I don't, all right? I don't want to delete it at the moment. At the upper portion, you can see you have the usual usual Excel options, but you also have this ProMax tab. And what's important for us is the scenario tool. And that's what we are going to use in a minute. So whenever I'm preparing a scenario tool, what I want to do first is prepare a table where I'm going to be saving my results. I always like to do a run count in my first column. Then in the next columns, I like to put my inputs. In our case, what I want to do, the only input I want to use at this moment is my amine flow. So this is what I'm going to be changing between the cases. But please note that you could also uh, have more input variables. So my units for the input for the amine flow are cubic meters per hour. So that's what I like to put here as well. And then I'm going to put my outputs. What I want to be checking for each run, I want to be checking the recovery, so the CO2 recovery, and the units for that is a percentage. And then the next thing I want to be checking is my SRD, so the specific reboiler duty. Sorry, I'll come over here, SRD, and that's going to be in the gigajoule per ton. All right, so this is the way I like to prepare my table. And then the next thing I will do is I'm going to come up with the numbers I want to use for the amine flow. So what I want to do just for this example is just to see what happens if I go down with my flow rate. And I just want to do a couple of 4 runs. And so I'm going to prepare the table like this. I have 4 runs, changing the amine flow rate, and this is this is the results I'm going to be watching. Now, to actually connect the Excel file with the ProMax variables, I'm going to click on the ProMax and Scenario tool, and I'm going to create a scenario. I'm going to give it a name. This is going to be my amine scenario. And I want to define what are my inputs and outputs. So for the ProMax input, I'm going to click Add Variable. I'm going to define it. So this is my amine flow. The moniker is the address of the object inside of ProMax, so I'm going to click Select ProMax Object. And now I'm going to navigate to wherever my amine flow is defined. So it's on this streams. Look, when I clicked it, it automatically opened it up, stream 25, and I'm going to go further, and I'm going to find property, which I can edit, and that's the standard liquid volumetric flow. Notice that it's written in bold, and that gives me the notice that this is a variable I can use. So it is possible to use it because it's actually an input variable in the model. All right, so anything which is an input variable in the model can be input through scenario tool. Once I click it, it's going to bring me back to my ProMax scenario tool log, and you can see the address here. And then I'm going to choose cell address, look that it changed it from B4 to B7. I'm going to check my units. It's cubic meters per hour, and that's it. I'm going to click OK. All right. So this is, I have just one input variable. Now I'm going to do the same for outputs. So I'm going to click Add Variable on the output. This is going to be my recovery, my moniker, select ProMax object. Remember that the recoveries, they're hidden in this recovery section, and it's going to be my MEA recoveries, and it's going to be, properties, and I want to be looking at how much is recovered in the acid gas stream for CO2. All right, so this is my recovery of CO2 in the acid gas stream. I can just click the set selection adjustment and it's going to move it over to the right. Percentage, that's okay, and I'm going to click OK. And the last variable is going to be my SRD. I'm going to click Select ProMax Object. Remember that this SRD is something I created a user value for. So I'm going to find my user value sets and I'm going to go for the specific reboiler duty. And I need to find the parameter. That's where the number is. And again, just moving it over, gigajoule per ton, that's what I want to do, and click OK. So now I've got inputs and outputs defined. I can see here runs from 1 to 4 are going well, and then I'm going to click Run. And what it's going to do, it will look into Excel, take the number 450, and then put it into ProMax, and it will update the model and it will give me the results in the output section. And the same goes for the second run and then following the rest. So this way we should have all the results automatically updated in the Excel file, and we will be able to see the trends, etc. So you can see now it's running the second run, and now we've got a result, and we can already see the trend, right? Lower amine flow, we get slightly lower recovery. We also get slightly lower SRD because we are circulating less amine, so we need to, there is less amine going through the regeneration section, and this way we will automatically get the results. So I strongly recommend everyone who every time you have to run more cases on the same model, don't do it manually with a paper writing down the results, but use the scenario tool. We have a great videos of how to use scenario tool in our tutorial section or on our YouTube channel. So I would definitely recommend you watching it or attend one of our hands-on classes, and we will teach you step by step how to use the scenario tool. And you can see the trend continues. The best thing about scenario tool, I can just drink coffee while it's running, or if you have a large case studies, it's something you can switch on in the evening before you go home, and then you come in the morning next day and you have a table full of results. The Excel file can then also be saved separately. So if I then use this file option and then save as, I can just save the table with the results separately outside of ProMax, and I can send it to anyone, even people who don't have access to ProMax licenses. All right. So really, I'm a big fan of scenario tool, and I'm sure once you start using it, you will be as well. All right, so you see it finished. It's giving me how much time it took, and I can see the trend. Now I'm in Excel, so it's very easy to plot, to make plots the usual way you're used to make plots in Excel. You can do any type of data analysis you're used to doing in Excel.
One thing which will always be used, is emission or losses control. So as I've showed you on the case of MEA, there was quite high MEA emissions. The same goes for the AMP piperazine case. So if I check this makeup stream, I'll be able to see that I'm losing quite a lot of AMP and quite a lot of piperazine. Definitely not something I want to do, right? And especially AMP piperazine, they're more expensive than MEA. So we don't want to have losses. And we don't want to send AMP and piperazine with our wet gas. So you can see this is the concentration of AMP and piperazine in our wet gas. That's something we don't want to have as well. So the way this is handled is that there is a water wash section being added at the top of the absorber. So we are circulating water here, and we are basically recirculating the blown down water back to our amine loop. So this way we are preserving the AMP piperazine. And you can see over here the difference between the AMP and piperazine concentrations in the wet gas and after the water wash. There are further process configurations which can help you bring down your specific reborder duty and in general optimize your carbon capture unit. One to mention is absorber intercooling. That can definitely bring down your SRD. The reason is that your absorber, and we could see it on the temperature profile in the absorber, you are going to get higher temperatures there. The reason is that the CO2 reaction with the amines is exothermic, so it's producing heat. If you want to help it, you want to do some intercooling in the absorber to get the temperatures down and help with the reaction. So intercooling can help you. Definitely stripper pressure optimization. So the operating pressure of the stripper has an effect, and it has a sort of a competing effect because the lower temperature at which you can operate the absorber, the lower pressure means lower temperature can be reached, and that can be reached, with maybe like a waste heat. It will also reduce solvent degradation if you're able to operate at lower temperatures. But of course, it also means the heat mass transfer is lower and the kinetics of the reaction are decreased. So looking at where is the best place in case of a stripper pressure, it's a very good thing to do. The loadings, the lean loading and rich loading numbers can definitely be optimized. And one last thing to mention is an interesting setup if you use a lean vapor compression. So in the bottom portion of the disturber, as you can see on this figure here, you can install LVC, and that will help you reduce your SRD. But what you have to, of course, think about is that you're introducing a compression work there. Now, this figure, I took it from a really interesting paper which was presented this year. You have the citation down there, and that paper, and maybe we have some of these authors present at our webinar today. If you guys are here, just raise your hand. But this paper provides really nice overview of how do the different process configurations improve the SRD. So when I went and I played quite a lot with the AMP piperazine model, and I added intercooler, as you can see how to model intercooler on this screenshot over here. And I played with the loadings. So I went and I operated the unit at a higher loadings, so higher lean loading and of course higher rich loading. I was able to get a CO2 recovery of about 93%, while the SRD was 2.8 gigajoule per ton of CO2. So that's where I got it. All right, so that was the aiming system part. And you see there is a lot going into it, a lot going into modeling it. And we are always happy to teach anyone on how to model these units in ProMax. You guys just have to attend one of our classes, and I will talk about that at the end of webinar. All right. Right now, I want to move on to the CO2 compression portion for the last portion of our webinar. So CO2 compression is basically a process where you're trying to take this captured CO2 with all the small impurities it has in it and compress it and maybe clean it a little bit more so it can be either stored or it can be utilized. And for the purpose of this, let's first have a little bit of theoretical talk, and then I'll show you how it works in the simulation. So as I said, the acid gas compression, we have a compression portion, we have a pipeline where we are sending it to the injection site, and we have the injection line if we are storing it, of course. The challenges there's numerous challenges. One is the non-aqueous, so the CO2 phase behavior itself. It has some challenges coming with it. The water content of the acid gas brings a lot of challenges. We have to be careful about hydrate formations, and we have to well understand the changes in the density and viscosity of the acid gas at the different conditions. The compression, usually we would use high compression ratios, typically about 3 to 5 stages. We are trying to keep the temperature at any case above the acid gas dew point or hydrate formation temperatures. We want to make sure we prevent hydrate formation. So either we apply heat or we are trying to remove the water naturally as much as possible. And I'll show you in a minute on how to do it. If necessary, we might need to use some further dehydration facility. So sometimes that would mean MOLSIF, or that in some instances, glycol dehydration unit can be used, but you have to be careful on what is your specification on the CO2 purity, which you are sending to the storage, because they might just tell you that it should have 0 ppm of TEG, which is not achievable if you use TEG units to clean it. And you might use inhibitors to prevent the hydrate formation. All of this can be modeled in ProMax. All right. Now, if we look at how does the water content change, you can see that as the pressure goes up, water content goes drastically down. At one point, you can see that there is a sort of a minimum of where you are, and then the water content goes up again. All right, you can see it on this graphic, and it's also affected by the temperature. It's very important to model this minimum correctly. So in ProMax, we have several thermodynamic packages which are able to do so, and I'll discuss this with you in a minute. What this figure is showing you, this is showing a comparison between GPSA data and a model done using the ProMax Peng-Robinson equation of state. And you can see that it's able to predict the minimums quite well. Now for the water content, you see that you're trying to design the unit such that the last compression stage is at the minimum of the water content, so that you remove the water naturally as much as possible. If we look at the operation in terms of phase envelope, we are operating in this region. We are trying to make sure that we are above the hydrate curve. And just at the end, we are crossing the phase envelope. And you see that here, the red line is going further up. You're increasing pressure and you're going to get into a supercritical region. So right now, what I'm going to do, I'm going to open a last example I have here. And let me actually, before doing that, close all the other examples for now. All right, so here is my example for the compression. So I've got a CO2 coming from our low pressure amine unit, but also from a little bit higher pressure unit. So I've got these two sources of CO2 going into this compression facility, where I'm compressing it and then sending it for injection. I promised you I'm going to discuss the different thermodynamic packages we have in ProMax. So we've got a couple ones which are very suitable for modeling CO2 dense phase. One is EOS-CG. EOS-CG is implemented in ProMax currently with the ability to model 6 components. In the next release of ProMax, in ProMax 7, we will have EOS-CG 2021, which is able to model 10 components. We do have GERC, which is able to model 21 components. And then, of course, we have our ProMax, Peng-Robinson, ProMax SRK, which the ProMax versions of these equations of state also do a good job modeling these systems. So depending on how many impurities you have in your CO2, you can go with either of them. Now, more information about the limits and usability of each is, again, if you go to our help page and you find the property packages. There is this, for example, EOS-CG model. And if you open it, you find some information about it, some references. And here is the list of the components it's limited to. But if you are able to fit your component list to these 6, then EOS-CG is the model to go with. That's not the case, then you can use GERC. GERC is limited to these 21 components. So if you're able to fit your component list, your CO2 impurities into these 21 components, you can go with GERC. If you have other small impurities which you need to model, then our recommendation would be our Peng-Robinson. All right? Okay, so right now my model is using a compression ratio of 3, so quite high. With that, I'm actually hitting very high temperature after the last compression stage, so 157 degrees, which is not something I would recommend because it could do problems to the metallurgy of your compressor, and it could also mean that you might not be able to cool it down in this cooler. So what I wanted to do, I would like to find out what my compression ratio should be in order to do the compression with the least amount of horsepower and to make sure that this temperature never crosses 150 degrees. But I also need to make sure that here in the underground, I'm hitting pressure of 260 bar G. Okay, so that's where I need to go, 260 bar G. So I have sort of an optimization case I need to do. Of course, I could do it manually, but you don't have to. That's always good, right? So I'm going to show you quickly an optimization tool we have where we can create a case. In this case will be my compression, where I'm going to say, hey, I would like, my objective is to minimize my horsepower. So what I essentially want to minimize is in my energy budgets, I want to minimize my CO2 compression power budget and net power. So that's what I want to minimize. I want to minimize the net power of my compressors. And how do I do it? I do it by figuring out what my compression ratio should be. So if I just go to my compression ratio and right click, I will add it to optimization tool. And here it is. So this is my compression ratio. And I have the model set up such that all the other compressors, they have the same ratio as my first one. So they will change accordingly. Then I want to make sure that this temperature which will be my T4. My T4 has a constraint of an upper bound of 150 degrees, which you see right now I'm not compiling with. I'm at 156. And I also want to make sure that this pressure, which is my P final, is at least, it has a lower bound of 260. All right? And that's what I want to do. I want to find out what my compression ratio should be and to make sure I hit the 150 degrees maximum after my last compression and that my final pressure is more than 260. And I wanted to try to figure out how to do all of this with the least amount of energy. So that's how I set it up. The optimization tool can be found here at the top, OPT. And then I'll click solve. And what it will do, it will on its own come up with numbers for the compression ratio, and it will on its own figure out how to best change it in order to achieve all of these constraints and in order to minimize my objective, so minimize my horsepower. Let's let it run for a few seconds, and it will find out on its own how it should be. And while it's doing, I'm just going to go and finish some of the slides. So last portion of this, I wanted to talk about storage. So you saw we compressed the CO2 and you can transport it either via pipelines or ships or trucks to your storage facility. Now, you will always be given a CO2 spec. So you will be told at what conditions and how pure, etc., you need to bring your CO2 at. And that will, of course, come with all the feeding and compressing upfront. Now, the storage, it can either be that you inject it into depleted oil gas fields, so deep saline aquifers. And I just wanted to mention some of the projects people talk about. So I think the most famous being the Northern Lights in Norway. Then we have Portus in the Netherlands, where it's going to be stored at the offshore depleted gas fields. And then in Scotland, there is the Acorn CCS, and in UK as well, it's the Net Zero Teesside. So all of these projects, they are going to be storing CO2. And I'm sure some of you know much more about this than me, and maybe some of you are involved with this. So if you want to share some of your knowledge, go ahead in the chat. We'll be happy to hear it. Now, one way is to store it. Second way is to use it. So use the captured CO2. And I would say the one usage which has been used for some time, especially in US and Middle East, is EOR, so enhanced oil recovery, where you inject the CO2 into the oil reservoirs to increase the oil production. The CO2 can also be used in building materials, so carbonation of cement, concrete. You can create synthetic fuels and chemicals. So for example, methanol. Methanol is produced, consumer, let's say, of CO2. And if you are interested in, let's say, methanol production, my colleague Philip has delivered a green methanol webinar a couple of weeks ago. There is actually a recording on our YouTube channel, so go ahead and definitely watch it. It can also be used in plastics and polymers manufacturing. Interesting one is the algae cultivation, where you actually transform CO2 into a biomass. And mineralization, of course, and then food and beverage. But in that case, it would have to be very pure CO2 and in small amounts. But those are the ways you can utilize it. And I think now let's go and see. It's still figuring it out. But you can see right now that it's trying to iterate. Now it already came with a successful step, and we can be looking at a graph as well. So it started over here where the constraints were not satisfied. Now it goes down, and it came up with a lower objective function with constraint satisfied, and it's going to try to optimize it this way. All right, so I'll let it work a bit more. And there's one more thing I wanted to mention on this model, is that on any stream in the model, in any kind of ProMax model, you can always find information and create and look at phase envelopes. So you would be able to create a phase envelope on the stream, and you would be able to see, am I already in a supercritical region? Because you would see you're above the phase envelope curve, right? So all of that can be found on any stream. And you see this is working towards its final. And it might be that it was actually able to find an optimum right away. This was, I would say, simple, straightforward optimization. But the optimization tool could be used to optimize any type of units. You can have multiple variables being changed at any time. You could use it on the carbon capture unit. If you want to do that, get in touch with me. There are some nuances to it I would like to share with you, but there is a possibility to use the optimization tool for any kind of unit. And so you see it's solved, completed, and it was able to bring it down with my constraint satisfied. And I can see that it's suggesting that I'm using the compression ratio of 2.7. All right, and with 10 minutes till the end, or the official end of our webinar, I'm going to go to my last slide. This webinar was, I would say, sort of a run through the processes and options there are. Now, don't forget that we have the example projects available for you. Most of the ones related to carbon capture, they will be found in the sustainability folder. A lot of the things you can find is in ProMax Help. So you saw I showed you a couple of the pages in ProMax Help. It's very easy to search through. We do have tutorial videos on our website and on our YouTube channel. And if this recording goes well, this video is going to be there as well. There are technical articles available on our website, free to read, free to go through. We have a support team ready to help you at any time, so you're always welcome to email us or call us at support@bre.com. Most importantly, we do teach free trainings. So of course, a lot of the techniques I showed you today, it's not something you could just learn, over a few minutes. It's something, it's good when you practice it hands-on, and we are happy to help you. We do teach online courses once in a while, and you're welcome to join that for sure. But I would definitely like to encourage you. If you and your colleagues would like to really get professional in using the tool and using the right tools, being able to model it correctly, let us know, and we will be happy to come to your offices personally. That option is also free of charge if you're a current customer, okay? So we can just schedule a day or two training. We will come to your office and we will help you get trained. So get in touch with us. And who to get in touch with? So as I said, I'm working from our European office. That's me on the picture on the left. I have two colleagues with me in our European office, Philip and Christian. Philip is working with our clients in France, Italy, Spain, and kind of the Southern Europe. Christian is working with you if you're in Germany or Netherlands or in Central Europe. Get in touch with us, schedule a meeting with us. We'll be happy to walk you through anything or explain you in more details any of the topics which were discussed. And the same goes with, I saw, guys, that there were a lot of really good questions coming into the chat. You do not have to wait for webinars to pose these questions, okay? So anytime you have a question, send us a message and we'll be happy to schedule a one-on-one Teams session or even come to your office and discuss it in person. And we can discuss any of your concerns or anything related to that.